What's up, everybody? It's Dan from SageMathTutoring.com, and I'm back with another video, this time about some sort of foundational probability concepts. Now, this video is for a student of mine. Now, my student, it's possible that um, this is going to be relatively easy. I think maybe the issue is primarily vocabulary. For example, we're going to talk about joint probability. We're going to talk about marginal probability. So it could be mostly a vocabulary challenge, but I say we just dive in. It should be a pretty short video. So, addition rules for probability. For occasions where we want to determine the probability that one or more of several events will occur in an experiment, the choice of a given rule would depend on whether or not the events are mutually exclusive. And I think my student at home realizes that mutual exclusivity means that basically, it means that the events can't happen at the same time. Okay. In other words, if one event is happening, by definition, it means that the other event is not happening. So, for example, if you're flipping a coin, the outcome of tails is mutually exclusive with the outcome of heads. Okay, so mutually exclusive. Okay, well, here's the definition. Occurrence of one means that none of the others can occur. The probability that one of the events will occur is the sum of their individual probabilities. Rule of addition when events are mutually exclusive. Yeah, so when event A and event B are mutually exclusive, then to find the probability of A or B, all you have to do is add the probability of A happening plus the probability of B happening. And you might notice that the word or, it's probably a good idea to start associating that with addition right away. Okay, looking at this, the breakdown of colors of cars made in North America during the 2004 model year, 20% of the cars were silver, 17% of the cars made were red. Okay, here we go. Probability that the car is either silver or red. I think, everyone watching this is going to be pretty easy. All you have to do is just, add the probability of it being red, which we'll call it probability of B, and we're going to add that to the probability of silver, which would be probability of A, and clearly that is 0.17 plus 0.2, and that equals 0. Looks like that would be 37. Okay, so hopefully that makes sense. 37% chance. Looking at the next one, probability that the car is either silver or some color other than silver or red. Okay, haven't specifically identified neither silver nor red with letter designation can be expressed as A prime and B prime. So this is interesting. I'm going to rely on what they give us. They're basically saying the event of neither silver nor red can be expressed as this sort of phrase right here. Okay. So the question that we need to ponder now is, okay, well, what is the probability of this? Okay. What is the probability of neither silver nor red? And for my student who's watching this, this is where the concept of complement is going to come in. The probability of neither silver nor red is going to be 100% minus the probability of silver or red. Okay. Now we already found that probability of silver or red is 37%. So the probability of not that, we could say, is going to be 100% minus 37%, and that is 63%, which I'm going to call uh, 0.63. Okay, so now we have to ask ourselves, okay, what is the probability that the car is either silver, which is sort of its own thing, or uh, or neither silver nor red. I mean, we're trying to figure out what's the probability of this thing or that thing. Ultimately, that's what the question is asking. So we could rewrite it in a formal manner where it would be the probability of silver, which is probability of A, and that's going to be plus the probability of neither silver nor red, which is A prime P of A prime plus B prime. And that's going to be probability of A, we already discussed, is 0.2, and the probability of A prime plus B prime, we just figured that out, is 0.63. So when you add those, that's going to be 0.83. Okay, so hopefully that makes sense. Looking at this one, a person randomly draws an M&M from a bag. There are 6 possible colors. The probability of drawing each color is as follows. Brown is 0.3, red, blah, blah, blah. What is the probability that the M&M is red or green? Well, I think my student who's watching this understands that's just going to be a matter of adding this one plus this one, right? So clearly that would be 0.3. And then they say, what is the probability of picking a blue M&M? Okay, interesting question, right? Because they did not list the blue one. They have a question mark right here, right? Well, the reality is that there are 6 possible colors, and here there are, or here they are, I should say. And the probability when you add all these mutually exclusive probabilities, when you add them, it should equal 1. Okay, it should equal 100%, you could say, or 1.0. So let's just call this x, and we could go ahead and just use algebra. Why not? We're looking at 0.3 plus 0.2 plus 0.2 plus 0.1 plus 0.1 plus x, and we know that that's going to equal 1. Now I'm going to go ahead and multiply everything by 10 because these decimals are annoying to me. We're looking at 3 plus 2 plus 2 plus 1 plus 1 plus 10x, right? Plus 10, okay? Adding all the like terms on the left side would be 5, 7, 8, 9. So we're looking at 9 plus 10x, and that equals 10. And let's see, 10x equals 1, and x equals 1/10, aka 0.1. And that is the answer right there. Okay. Now, for my student who's watching, did you have to do the thing where you multiply everything by 10 and turn it into this situation? Absolutely not. You could have literally just have combined like terms over here, and it would have been like decimal stuff, and gone through the motions, and you would have still arrived at that answer. Okay, so the probability of picking a blue M&M is 0.1. Okay, looking at the next slide, if events are not mutually exclusive, 2 or more events can happen at the same time, and the general rule of addition is this. So if the events are not mutually exclusive, there's still going to be some addition going on, right? We're going to be adding the probability of one thing plus the probability of the other thing, but then you have to subtract what you could consider to be the intersection of those 2 events. You have to subtract the probability of both of the things happening at the same time, okay? And the reason for that is because by adding this probability and this probability, you've actually um, uh, added this part twice, okay? And you have to subtract away one. I don't know, it's probably better with a Venn diagram. So basically, imagine you have this overlap here. Here's the area where both of the events are happening at the same time. Maybe this is A, maybe this is B. When you're trying to figure out the probability of A or B, well, let's kind of draw it again. The probability of A could be represented by taking into account this entire shaded region here. That's the probability of A happening. And then if you want to know the probability of B happening, well, you would be taking into account this shaded region. But if you look closely, what we've done is we've counted this middle part twice. So you have to get rid of one of those intersections there that you had counted twice, okay? And that's what we're doing here. So there are ways using Venn diagrams to sort of understand why you have to subtract this away. So anyway, let's see. Can also be applied when events are mutually exclusive. Final term will be 0 because the events that are mutually exclusive cannot happen at the same time, right? Exactly. So basically, in a way, the previous equation that the professor gave for mutually exclusive events, it's really the same formula. Okay, it's really the same formula. It's just that this part happens to be zero. That's all. Okay, so that's kind of interesting to note. By looking at the next part, when events are independent, the joint probability is the product of their individual probabilities. Multiplication rule when events are independent. Okay, well, first of all, independent means that the outcome of one thing is not affected by the outcome of the other thing. Okay, so for example, if I am rolling a dice and then I'm flipping a coin after that, well, the outcome of the coin flip has nothing to do with and is completely unaffected by the roll of the, I guess I should say die, right? The roll of the die. I think that's it. I don't know. Dice, die. Maybe just check that. But I think you understand what I'm saying. One outcome does not affect the other, and therefore they are independent events. Now, whenever events are independent like that, well, you can just multiply the probability of each thing, and then you're going to have the probability of both things. So we call that the joint probability. Okay. Okay, whenever events are not independent, then we're dealing with what's called conditional probability. And that has to do with the occurrence of one will influence the probability that another will take place. Okay, now the way to read this is, let's say event A and event B are not independent, then it's the case that you're going to be multiplying the probability of the first thing, A, times the probability of B, given the fact that A has already occurred. So this vertical line here should be read as given that. Okay, maybe my student who's watching this can recognize that that vertical line means given that. Okay, so probability of B given that A has already occurred. And that makes total sense. I mean, look, if we are calculating probabilities having to do with a deck of cards, well, you could say that K represents drawing a king. Okay, and we could say Q represents drawing a queen. Okay, and it's without replacement, meaning you take a king out, but you do not put it back in. You leave the king outside of the deck. Well, if you want to know the probability of K and Q, meaning you draw a king, then you draw a queen, that would be the probability of the king times the probability of drawing a queen, given that you've already drawn a king. And just by sort of, thinking it through, this would be 4 over 52, and we'd be multiplying that by, there's 4 queens in a deck, so that'd be 4 over 51. Okay, so notice the 51 because we're taking into account the fact that the king has already been drawn, so there's only 51 cards in the deck left over at that point. So then you, of course, can multiply that, and that would be 16 over 2652, and that reduces to 4 over 663. Okay. Okay, so that is how that works. Now, the only other thing I'll say to my student is that this is the equation for the probability of A and B if the events are not independent, but can you see how this can be rearranged to also say the probability of B given A is equal to the probability of A and B over the probability of A, okay? Now, how did I do that? Well, I literally just isolated this by dividing both sides by the probability of A, okay? And in doing so, these cancel, and then we're left with this, and I just switched it around, okay? So this original sort of equation that the professor gave in the notes is definitely useful. And I will say for sure that occasionally you might need to find the probability of B given A, in which case you're going to rely on this sort of setup here, okay? Perhaps in the word problem, they tell you what the probability of A and B is, or maybe you have a two-way table or something where you can clearly see what the probability of A and B is, okay? Now, what do I mean by two-way table? Let's say we have male, female, or more than two-way table. It could be more than a two-way table. But let's say we have male and female, and we have math majors and theater majors, okay? And those are the only two majors in the school. Imagine that, right? Well, the marginal probability over here would be 1. And by the way, marginal probabilities are the probabilities off to the side of a two-way table and on the bottom of the two-way table. Okay, that's something I had forgotten to mention. So let's say the probability of let's just kind of do the marginal probabilities first. Imagine this is true. Imagine this is true. Okay. Notice how when you add 0.7 plus 0.3 equals 1, 0.6 plus 0.4, that also equals 1. And let's go ahead and imagine that this is 0.1, which makes this 0.5, which would make this 0.2, which would make this 0.2. Okay, so it's almost like solving a puzzle, like a Sudoku puzzle or something like that. So bottom line is, this is a two-way table, and let's say you were calculating what's the probability of male and math major. Okay, let's say that that's what you're looking for. Well, that's this right here. Okay, that's the probability of being a male and a math major at the same time. It's given by the two-way table. You don't have to do anything too fancy there. So if you wanted to know what's the, let's say, based on this formula here, let's say we wanted to know the probability of being a math major, given that you're male, well, we could totally rely on this setup here, where it would be the probability of being a male and math major, right, which we just talked about. And that would be all over the probability of being a male. Okay, so what would that look like in this data set? Well, we already know that the probability of being male and a math major is right here. That's 0.5. And we're going to put that over the probability of being a male in general. Now, that probability is found in the marginal probability. That's down here. All right, so that's going to be 0.7. Okay, that's the probability of being a male just in general. So we are looking at 0.5 over 0.7. If you plug that into your calculator, that would be approximately 0.71. Okay, 71%. Okay, so hopefully that makes sense. Just remember, you could realize this equation, but you could also realize this equation depending on what your needs are. So anyway, to my student who's watching, good luck, and I will talk to you later. Take care.